the launch for week 3, we looked at approximating a function with polynomials. And there the purpose was to show that if you picked the basis for your problem right, then the matrix ended up being much nicer. In this week, we're going to look at how to solve the problem. In general, if you try to, for example, fit a line to 4 points, just eyeballing this, the line is not going to be able to go through all 4 points. So the best you can hope for is a line that best approximates the data. And in this week, we're going to talk about what best means and how to find that best solution. Now, to do this, we changed things slightly. In week 3, we looked at f of a variable chi, which was equal to some polynomial. And here we chose that polynomial to be of degree 1. In other words, we're saying that f is equal to a line. Now, in general, of course, it's not exactly equal to a line. It's approximately equal to a line. We're going to change the variables that we use slightly. We're going to use alpha instead of chi, and we're going to use chi instead of gamma. And why we do this will become clear momentarily. So what we really want is we want a function of alpha, which we approximate roughly with this line, except the variable that we use is alpha. And therefore, when we labeled our points, we used alpha 0, beta 0, instead of chi 0, phi 0, which is what we did in week 3. Now let's have a look at this. If we could go exactly through all of these points, then these 4 linear equations right here would all be simultaneously satisfied by the solution. Okay. Now, again, eyeballing this, we're not going to get it exact, and therefore the best we can hope for is finding the coefficients that best fit the data. We can capture these 4 equations in 2 unknowns with this right here. All we've done here is we've set it up as a matrix times a vector of those 2 coefficients, chi 0, chi 1, equal to some right-hand side, beta 0 through beta 3. All right? And now it becomes clear why we chose alpha and beta here and why we chose chi for our coefficients, because now we can label this as A, we can label this as X, and we can label this as B. And ideally we would exactly solve this, but what we notice is that we can only approximately solve this. Right? If we go back over here, then notice that we can drop this point down to the point on the line, and notice that that point still has the first coordinate alpha 0, but the second coordinate now is beta 0 hat. And then here we can drop this down to the line, and that would be alpha 1, beta 1 hat, and so forth. Okay? Now, all of those points are actually on the line. So all of those points we can exactly solve for X with matrix A. All right? Now, the question now becomes, which line is best? Well, these distances here tell us something about how good the line is. So one thing we could say is, well, we want the sum of these distances to be minimized. In that case, you would be minimizing beta 0 minus beta 0 hat, and then beta 1 minus beta 1 hat, and so forth. And if you look at this, you see, oh, wait a minute, we can more succinctly write that as b minus b hat in 1 norm. So we're trying to minimize the one norm of the difference between these two vectors. Now, when you try to minimize, what did you learn in calculus? You take the function, you differentiate it, you set it equal to 0. But that means that the function has to be differentiable. And notice that the one norm is actually not a differentiable function in general. So for that reason, people actually use the square of the 2 norm and minimize that instead. And all of a sudden it becomes clear why people call this solving the linear least squares problem. Because you're solving the problem of minimizing the sum of the squares between the solution, or the best solution, and the actual points that you started with. Okay? So the way you can state this is you're trying to minimize the 2 norm of b minus b hat in 2 norm, and you can drop the square because whether you minimize the 2 norm or whether you minimize the square of the 2 norm, you get the same answer. If we then go and say, oh, wait a minute, in this particular case, a times x is actually equal to b hat, right? Because these points are actually on the line. Then what you're really doing is you're saying minimize over all x b minus a times x in 2 norm. And you're trying to find the x that actually minimizes that because you're interested in these coefficients. This week is all about how to solve linear least squares problems, the theory of linear least squares problems, and how to use some of the factorizations that we have seen in previous weeks to practically solve linear least squares problems. And it turns out that linear least squares problems are at the core of data science, and any time in other sciences you use data.